warm welcome to all present in this meeting. On behalf of the Department of Mathematics at Wilson College, Mumbai, I heartily once again welcome Dr. Akshay Kumar sir for his session in this IIT JAM Mathematics Lecture Series organized under the DBT Star Strengthening Scheme. Sir needs no introduction. He has very graciously accepted our invitation again and agreed to do more sessions on the based on the request that we received from the participants. Sir is an assistant professor at the Department of Mathematics of Vellore Institute of Technology, Amaravathi, Andhra Pradesh, India. And his areas of interest are in functional analysis and its application to function spaces. So thank you so much for taking out your valuable time to share your expertise. I now invite Sir to start his session. Thank you.
Yes. Thank you, ma'am, for the introduction. Okay, let me share my screen. Okay, is my screen visible to you?
Yes, sir. Yes, it is visible and showing the last uh, written note on the board.
Okay, so yesterday, day before yesterday, we were doing this question. So suppose you have A and B two matrices of rectangular matrices of order n cross n, and we were proving. So if 0 is an eigenvalue of AB, then 0 has to be an eigenvalue of BA. This is only this statement only holds if we have the rectangular matrices n cross n, square matrix n cross n. Okay, so let me write these things again. So suppose 0 is an eigenvalue of AB. Now what we want to prove? So 0 is an eigenvalue of BA. Okay, now suppose 0 is a now since 0 is an eigenvalue of AB, so for some V not equals to 0, what we can write? AB V has to be 0, right? Now we can make two cases if B is non-zero or BV equals to 0. Okay, now if BV is not 0, then we have no issue, because what we can do, BA just operate on BV. So what we will get, B of AB V equals to, so this is 0, so B 0 equals to 0, right? Now the only issue is what will happen if BV equals to 0. So in this case, what we can do, so in this case, nullity of B, this is what I was trying in the last session. So nullity of B will be greater than equals to 1, right? So rank of B in this case will be strictly less than n, right? So
Yes, sir.
can you tell me what will be the rank of BA?
Minimum of rank B and rank A.
So
It
it
will
will be
be
less than,
minimum.
strictly less than n, right?
N. Yes, yes.
Because rank of B is strictly less than n. So in this case also there exists some W non-zero such that B of A BA W equals to 0,
Yeah.
right? So this implies 0 is also an eigenvalue of
B.
BA.
Thank you, sir.
So, so this is what we were proving in the last time. Okay, now let me start with the similar matrices. So what are similar matrices? Suppose you have matrices A and B, of course square matrices. We say A and B are similar matrices if A equals to P inverse B P. For some invert, of course, we are writing P inverse, so P is an invertible matrix. Right. If this hold, then we say both A and B are similar matrices. Okay. And if a matrix A is similar to a diagonal matrix, then we say this matrix is diagonalizable. Okay. So the thing you should prove here is if A and B are two similar matrices, then both A and B have same eigenvalues. Okay, since they have same eigenvalues, what you can write is both A and B have same trace and same determinant. So maybe this is, it's not difficult to prove, you just prove this. It is not difficult to prove. Okay. 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 So what are the natural choice for this matrix D and P here? Suppose we are saying A is a diagonalizable matrix. It is may not be a diagonal matrix, but it is diagonalizable. Then what are the natural choice for D and P? Since we are writing A is diagonalizable if A is similar to diagonal matrix, right? So this is diagonal matrix, DP is invertible matrix, right? So similar matrix A and D will have same eigenvalues. So the natural choice for the entries of D will be the eigenvalues, and the other entries will be 0 since it's a diagonal matrix. Now, how will you calculate P matrix, the invertible matrix? You just calculate P equals to, so the corresponding eigenvectors. So corresponding to lambda 1, we will have some eigenvectors. You just take x1, x2, eigenvector xn, such that all should be linearly independent. Okay. So in this case, you can see that AP will be equals to PD, right? So A equals to P, D, P inverse. So this is how you will get P and D. Okay, let me take some example. So suppose your A is 0, -2, 3, 5. Okay, now what are the eigenvalues for this? So eigenvalues lambda 1 plus lambda 2, sum will be trace. So 5. Now what is the product? Lambda 1 plus lambda 1 into lambda 2 will be equals to 6. This is the determinant. Product of eigenvalues equals to determinant, and the sum of eigenvalues equals to trace. Now can you tell me what is the value of lambda 1 and lambda 2? So it will be 2 and 3 if you solve this. 3 plus 2 5, 3 into 2 6. Right. Now corresponding to lambda 1, so if you take lambda 1 equals to 2, so from lambda 1 and lambda 2, what you can get your diagonal matrix D. Okay, you don't know whether this matrix is diagonalizable or not. Okay, for that, okay, let me do first for some result. So a matrix A is if and only if so the following are equivalent. So a matrix A is diagonalizable if and only if for every eigenvalue lambda, the algebraic multiplicity of lambda is equals to the geometric multiplicity of lambda. Okay, what is the meaning of algebraic multiplicity? The how many times lambda is coming as a root in the characteristic polynomial. This is algebraic multiplicity. What is the geometric multiplicity? This is the nullity of a minus lambda I. So this is the geometric multiplicity. If for each eigenvalue lambda, if the geometric multiplicity and geometric multiplicity are same, then A has to be diagonalizable. Okay. So third statement is, so for suppose the eigenvalues are lambda 1 and lambda k. Distinct eigenvalues are lambda 1, lambda 2, lambda k. Okay. Then the geometric multiplicity of lambda 1 plus geometric multiplicity of lambda 2 plus geometric multiplicity of lambda k. So the sum of all the geometric multiplicity of eigenvalues has to be equals to n. The order of matrix A is n cross n. So if these three statements are equivalent, okay, so this one 2 and 3 proving to prove this one is very easy. Okay, and if you and this one you can prove by using this fact, by like D will be your eigen entries will be your eigenvalues on the diagonal, and P will be your eigenvectors. Like this, by using this fact you can prove one if and only two. Okay, now so what you can write from this statement, now the corollary is, now suppose you have a matrix A and it has all distinct eigenvalues. Suppose all eigenvalues of A are distinct. So eigenvalues will be lambda 1, lambda 2, lambda n. All are distinct. So what will be the geometric multiplicity of lambda 1? I told you geometric multiplicity of any eigenvalue will always be greater than equals to 1 and less than equals to algebraic multiplicity of lambda. Right. So since all the eigenvalues are distinct, so algebraic multiplicity is 1. So for all like eigenvalues, geometric multiplicity are 1. So geometric multiplicity of lambda 2 plus so on geometric multiplicity of lambda n. So the sum will be 1 plus 1 plus 1. These are n times, so it has equals to n. Right. So if all the eigenvalues are distinct, then this will imply A has to be diagonalizable. Okay. Now come to this question. So eigenvalues are 2 and 3. So it is diagonalizable, right? So how will you construct D? So this will be 2, 3, 0, 0. At the diagonal entries, just put the eigenvalues, and since it is a diagonal matrix, other entries will be 0. Right. Now corresponding to the eigenvalue lambda 1, calculate the eigenvector. So what will be the eigenvector? A minus lambda I. So it will be A minus 2I. So if you write this, it will be minus 2, minus 2, 3, 3. Now what if you find so if nullity, so null space will be minus 2, minus 2, 3, 3, and null space will be x1 x2 equals to 0 0. So the null space of this a minus lambda 1 I will be equals to span of the vector. Now if you see this one, the first equation, you will get x1 plus x2 equals to 0. From the second also you will get the same equation. So 1 minus 1. So the eigenvector is 1 minus 1. Right. Similarly, if you do for the lambda 2 equals to 3, if you do the same thing for lambda 2 equals to 3, then what will be the a minus 3I? It will be, what is matrix A? 0 minus 2 3 5. 0 minus 2 3 5. So if you write this a minus 3I, you will get minus 3 minus 2 3 and 3 2. Right. So you will get null space of this will be equals to, if you write the equation, you will get 3x1 plus 2x2 equals to 0. So it will be span of the vector 1 and minus 2 by 3. So now your D is 2003. So what will be your P? The eigenvectors. Eigenvectors are 1 minus 1 and 1 minus 2 by 3. So if you calculate AP, then it will be equals to PD. So A is diagnosable. So this is how you can calculate P and D. Okay. Now for a 3 cross 3 matrix, you can take any example and solve that equation. Solve that example. Okay. Now how this diagnosable will be useful. Now suppose, so you have a matrix A. Importance. Suppose you have any matrix A. So how will you calculate A to the power, say 1025, 6, some 7, something like that? How will you calculate? But if your matrix A is diagonalizable, then what you can do, you can write A as P D P inverse. Right. So what will be A square? There will be P D P inverse, then P D P. So it will be P D square P, or P inverse. Right. Similarly, if you will do A to the power K, it will be P D to the power K P inverse. Right. So once a matrix is diagonalizable, it's very easy to find the power of that matrix. So in this case, if this matrix is diagonalizable, then A to the power 10256 will be equals to P D to the power 102567 P inverse. Right. Now what is what is the power of diagonal matrix? Suppose this is your diagonal matrix, lambda 1 lambda 2 0 0. So what is D square? If you solve this, you will just get lambda 1 square 0 0 lambda 2 square. So what is D to the power K? D to the power K will be lambda 1 to the power K 0 0 lambda 2 to the power K. Now multiplying diagonal matrix is very easy, but multiplying an arbitrary matrix is very tough. So if matrix is diagonalizable, then by using this property A equals to PDP inverse, we can find any power of that matrix. It is very easy to calculate the powers of that matrix. So this is one of the importance of diagonalizability. Okay, this is one of the importance. Okay, so since you already know what are matrices. Matrices are just linear transformations, right? Suppose you have a linear transformation from V to V, right? When will you say this linear transformation is diagnosable? So you will say this linear transformation is diagonalizable. This linear transformation is diagonalizable if there exists a basis B of V such that the matrix of this linear transformation corresponding to the basis B is a diagonal matrix. It is not for all the bases. It is there exists some basis corresponding to that basis. Your matrix representation will be a diagonal matrix. So if this hold, you can say your linear transformation is diagonalizable. Okay. Now suppose you take any other basis D of V, right? So and if you calculate the matrix representation of T with respect to D, so this matrix may not, if your linear transformation T is diagonalizable, then this matrix representation may not be a diagonal matrix, but it will always be similar to a diagonal matrix. Now the question is, suppose T is a linear transformation from V to V, and we know this is diagonalizable. Now suppose I take two different bases, B and D. Right. What you can say about this matrix representation P to D? Will it be similar to a diagonal matrix? So I can tell you the answer because we don't have much time. So the answer is no, and your work is to just find the example for this. Okay, if you change the basis in domain and codomain space, that matrix representation may not be similar to a diagonal matrix. Okay, and your work is to find the example for this. Okay, now let me give you some more characterization for diagonalizability. So for that, let's do first minimal polynomial. Okay, so suppose you have a matrix A and cross n, right? And you just find it's a characteristic polynomial, that is P x. Suppose this we are denoting this as Px or P lambda. You can take whatever you want. Okay, so what property this polynomial has? So this polynomial will always satisfy this matrix. This matrix A will always satisfy this polynomial. So the meaning is P of A will always be equals to 0. Okay, so this is called Cayley-Hamilton theorem. Okay, so your matrix A will always satisfy its characteristic polynomial, right? Now, what are the roots of this polynomial? Just eigenvalues. Okay. Now, what we are looking for? We are looking for the minimal polynomial of this kind. That will be our minimal polynomial. Okay. So our minimal polynomial will be. So what is the definition of minimum polynomial? So minimal polynomial. So a polynomial mx. So such that m of a equals to 0. So first condition. Second condition. So all eigenvalues.
Sir, can I say
Yeah. Tell me.
hello?
Yeah. Hello? Am I audible?
Yes, sir. You are audible.
Okay. Someone was saying something.
Yes, sir. Am I audible?
Yeah, yeah.
Yeah. And up to this thing, have you defined polynomial? Sorry, polynomial, minimal polynomial or not?
Which one? I'm defining a polynomial mx is said to be a minimal polynomial for
Hello,
matrix
sir.
A if
Hello.
m of A equals to 0 and all eigenvalues are roots of mx, and third condition is if any polynomial qx satisfies condition 1 and 2, then mx has to divide qx. So if a polynomial satisfies these three conditions, then that polynomial is said to be the minimal polynomial of A. Even you can prove that this polynomial will be unique. That's why we are calling it the minimal polynomial. It is not a minimal polynomial, it is the minimal polynomial. It will be always unique. Okay, if a polynomial satisfies all these three conditions, then that polynomial is called minimal polynomial. Okay. Now, so from the third condition, can't we say, so from the Cayley-Hamilton theorem, we know P of A equals to 0, right? And we already know P, the characteristic polynomial always satisfy the second condition also, right? So we can say the minimal polynomial will always divide characteristic polynomial. So this is your characteristic polynomial. This is your minimal polynomial. Okay. In general, the general form of minimal polynomial will be, suppose lambda 1, lambda 2, lambda k are the distinct eigenvalues of a matrix A. So in this case, I'm only taking distinct eigenvalues. I'm not taking all eigenvalues. If I am taking all eigenvalues, then that the index has to go up to n, because the order of matrix A is n. But now I'm only taking distinct eigenvalues. If lambda 1, lambda 2, lambda k are distinct eigenvalues of A, then the general form of mx will be x minus lambda 1 to the power r1, x minus lambda 2 to the power r2, so on lambda minus x minus lambda to the power lambda k to the power rk. So this will be the general form of minimal polynomial. Remember that the second statement is not the exactly roots of minimal polynomial are eigenvalues. They are not no other roots other than eigenvalues, right? So that's why the general form will be like this. Okay,
Sir, what is R1, R2, and RK?
they will be integers, positive integers, like natural numbers. Positive integer means natural numbers, they will be.
Okay, sir.
Okay, suppose you have matrix A 2 1 0 2, right? So can you tell me what are the eigenvalues for this matrix? What are the eigenvalues for this matrix? It is a triangular matrix 2 2, right? Am I audible?
Yes, sir.
Okay. So these are the eigenvalues of A, right? So what will be the characteristic polynomial for this? The characteristic polynomial will be x minus 2 to the square. So this is the characteristic polynomial, right? Because it has only two roots and that those roots are 2 comma 2, right? Now minimal polynomial will always divide characteristic polynomial, right? So our minimal polynomial has to divide this polynomial x minus 2 the whole square. So there are only two possibilities. So either the minimal polynomial has to be x minus 2 or x minus 2 the whole square, right? These are the only two polynomials which divides x minus 2 the whole square, right? Suppose take this example, take this case. Suppose our minimal polynomial is mx equals to x minus 2. Now the first property of minimal polynomial says that matrix has to be satisfy its minimal polynomial. So m of a will be equals to a minus 2i equals to 0. So a has to be equals to 2i. But this is not our case, right? So this condition, this case is not possible. So the only case which is possible is this one. So this is our minimal polynomial. So in this case, minimal polynomial is x minus 2 to the square, right? Okay, let me tell you one more result. So a matrix A is diagonalizable if and only if your minimal polynomial will be in the linear factorization. What is the meaning of that? The value of R1, R2 and Rk will be 1. So your minimal polynomial will be x minus lambda 1 into x minus lambda 2 into x minus lambda k. The value of powers will be 1. So it is if and only if, right? Now suppose I give you this matrix A 1 2 3 0 0 0 0 0 0. So can you tell me what is the minimal polynomial for this matrix? This is a diagonal matrix, so of course diagonalizable. Okay, 0 3, sorry.
X
Even
minus
if you
1,
want,
x minus 2, x minus 3.
correct, x minus 1 into x minus, okay, let me write here. So minimum polynomial will be x minus 1, x minus 2, x minus 3, because this matrix is diagonalizable. Even this matrix is itself diagonal, right? So the minimal polynomial will be in the linear factorization, right? And minimal polynomial will contain all roots of your means if your eigenvalues are there, so all eigenvalues will be root of minimal polynomial. So 1 2 3 has to be root of minimal polynomial, right? So this is the only possible case. Okay, now suppose you take this example 2 2 2 0 0 0, then you make it one here, one here. This is only this one is okay. Now what are the eigenvalues of this matrix? 2 2 2, right? Correct, because it is a triangular matrix. It is a triangular matrix, so eigenvalue has to be equals to diagonal entries. So you will get only 2 2 2, right? Now, so what will be the characteristic polynomial for this matrix?
X minus 2.
To the power 3, right? Because 2 is the only eigenvalue of A. right? Now, so what will be the minimal polynomial for this? So possible minimal polynomial is either it will be x minus 2,
X minus 2,
x
x
minus
minus
2
2 whole square,
square,
and x minus 2 whole cube.
x minus 2 whole cube, right? So take this case. So if mx equals to x minus 2, then by the first property, ma equals to a minus 2 I equals to 0. A has to be satisfied its minimal polynomial. So if you see this one, so a equals to 2i. But this is not our case. This is not true. So this is not our case. Now only options are second one and three one. Second and 3, right? But in both the cases, your minimal polynomial is not in the linear factorization, right? In this case also, in this case also, powers are not 1. So it is not in linear factorization. So from these two cases, you can say this matrix will never be diagonalizable. Because a matrix is diagonalizable if and only if its minimal polynomial is in the linear factorization. But now in this case, only second and third case is possible. Even if you take this case, second one, then you will get a contradiction. So only the minimal polynomial is the third one, x minus 2 to the power cube, right? So like this, you can figure out a matrix is diagonalizable or not. Okay, now let me make it a matrix A 2 2 3 0 0 0. Okay, then 1 0 0. Now in this case also, so what will be the eigenvalues for this matrix?
2,
2
2, 3.
2 3. Now what will be the characteristic polynomial? X minus 2 square x minus
X minus
3,
3.
right? Now what will be the minimal polynomial? Now, possible cases, so it will be either x minus 2, x minus 3, because it will take all the roots, and it will, the second thing which is possible is x minus 2 square x minus 3. These are the only two possible cases, right? Now if you take this case, if you take mx equals to x minus 2 x minus 3, and if you calculate ma, now what is a minus 2i? Okay, we will calculate this, and a minus 3i. Now you calculate a minus 2i. What is a minus 2i? It will be 2 minus 2 0 1 0 0 0 0 0 0 1, right? What is a minus 3i? So minus 1 1 0 0 minus 1 0 0 0 0, right? Now if you see, multiply this matrix, what will happen? You take the second entry, you see the second entry, a 1 2. So first row, second column. So is it 0? Is it 0 or not?
No,
No,
sir.
sir, it's
No, sir.
minus 1.
No. So the matrix is not equal to 0. So this is not equal to 0. So this, so minimal polynomial is not equal to this case. So the only case which is remaining is mx has to be equals to x minus 2 square x minus 3. Again, in this case also, your minimal polynomial is not in the linear factorization. So you can clearly say this is not diagonalizable.
Sir,
Yeah,
sir, why do not take x minus 2 single, but
because if you take only x minus 2, mx equals to x minus 2, then 3 is not a root of this polynomial. Minimal polynomial, the roots of minimal polynomial will always be all eigenvalues.
okay, sir.
Your minimal polynomial will always have roots like as your eigenvalues. It may be in the algebraic multiplicity may not be the same as characteristic polynomial, but it will contain all the eigenvalues as a root. So this is the second statement, right? So all eigenvalues are roots of minimal polynomial, right? So it cannot be x minus 2 because 3 is also an eigenvalue. So from this we will not get 3 as a root. So we have to add x minus 3 here. Right? This is the reason. Okay.
Yes, sir.
Okay. Okay. What else you can do? Okay. Suppose you have a matrix A, nilpotent matrix. Let's take nilpotent matrix, and a to the power k equals to 0. Right. Now, can you tell me what are the eigenvalues of for this matrix A? This A matrix A satisfy this condition, a to the power k equals to 0 for some k greater than equals to 1. Okay. Now, what can you tell me what are the eigenvalues of A? What are the eigenvalues of this matrix?
K,
Sorry,
K cross K.
A cross A.
Or
Eigenvalues of this matrix A.
So
sir,
0 can
0.
be
0, 0, 0. All eigenvalues will be 0. Right. So, why?
Yes, sir.
Now, suppose lambda is an eigenvalue of A, then lambda to the power k will be an eigenvalue of a to the power k. So, since a to the power k equals to 0, then lambda to the power k has to be 0. Right. What are the eigenvalues of a to the power k? Because it's a 0 matrix, the diagonal entries are 0. So, lambda to the power k has to be 0. So, lambda has to be 0. Right. So only possible eigenvalues for nilpotent matrix are 0. Now, here you have two cases. First one is either a equals to 0. If your k equals to 1, then a can be 0. Right. Second case is if k is strictly greater than 1. So a is not equals to 0. A is not 0, but for some k, a to the power k is 0. If a is 0, then you can take any power of a, it will be 0. Right. So these two cases are possible, right? Either a will be 0 or a is not 0, but some power of a will be 0. Right. Now in this case, clearly a is a 0 matrix, so it is diagonalizable. Even it is a diagonal matrix. Right? Because it itself it is a diagonal matrix, 0 matrix. Right. Now suppose a is not 0. Right. So can you tell me what will be the characteristic polynomial for this case? A is an n cross n matrix. You already know the only possible eigenvalues are 0. So what will be the characteristic polynomial? X to the power n only, right? So what is the characteristic polynomial? So suppose lambda 1, lambda n are the eigenvalues. So your maybe some values may be same. So what will be the characteristic polynomial? It will be x minus lambda 1 into x minus lambda 2, x minus lambda n. Now all the eigenvalues are same and equals to 0. Just put lambda 1, lambda 2, lambda n equals to 0. So what you will get? Px equals to, you have n times x. In multiplication, you will have x to the power n. This is the characteristic polynomial, right? Right? Is it clear?
Yes, sir.
Okay. Now, so what are the possible cases for minimal polynomial? Either it will be x or x square, x cube, so on up to the x to the power n. Right? Now take this case. So if mx equals to x, then from the first property, ma has to be, it is equals to a and it has to be 0. But what we have taken, a is non-zero. Right? So this case is not possible, right? So this is the only case in which your minimal polynomial can be in linear factorization. In other cases, your minimal polynomial are not in linear factorization. Right? So your minimal polynomial is not in linear factorization. So your matrix is not diagonalizable. Okay. So if your matrix A is non-zero but nilpotent, then your matrix A cannot be diagonalizable. Right? This is the reason why it is not diagonalizable, because your minimal polynomial is not in linear factorization. Okay. Now similarly, you can take some other cases also. Suppose you take other example. Suppose you have a square equals to a. So what you call these matrices? Idempotent. To take any idempotent matrix, right? So what will be the eigenvalues for this matrix? What will be the eigenvalues of matrix A?
0 and 1.
Yes, lambda square equals to lambda. So lambda square minus lambda equals to 0. So lambda is either 0 or 1. So if lambda is an eigenvalue of A, then lambda will be an eigenvalue of A square. Right? Lambda square will be an eigenvalue of A square. So lambda square equals to lambda. So you will get either 0 or 1. So the only possibilities are 0 and 1. Right?
Yes, sir.
Okay. Now, so what you can write is, okay. So what can you say about the characteristic polynomial here?
X into x minus 1.
So some power of x, so x to the power k into x minus 1 to the power n minus k. Right? Because you need n roots in characteristic polynomial, you need n roots, right? So in some, like in k places you will get 0, and at the remaining places you will get 1, right? So this will be the characteristic polynomial. Okay. Now suppose you take this polynomial. So is qa equals to 0? Is qa equals to 0? Because a square equals to a, right? So q of a equals to 0, right? Q of A equals to 0.
Yes,
So A satisfies
sir.
this polynomial. Right. Now, what is the property of minimal polynomial? It always divide the polynomial which take roots of eigenvalues and satisfy matrix A. Now, what are the roots of this polynomial? 0 and 1. It takes all eigenvalues and also satisfy A. So mx has to divide qx. Although it may not be the characteristic polynomial, but it contains all the roots. It contains all the eigenvalues as the roots, and it also satisfies the matrix. Right. The second condition, q of a equals to 0, and it also has eigenvalues as the roots of the polynomial. So mx has to divide qx. So what are the possible cases for minimal polynomial? So if you write this, you will get x into x minus 1.
So only x into x minus 1 is possible.
So x into x minus 1. This is the only possible case. Right. Now what you can say about after looking at this equation? A is
Diagonal algebra.
yeah. We don't know what is the matrix. We only know matrix satisfy this property. And after looking at the minimal polynomial, what we can say is diagonalizable. Right. Now suppose take some other example. You take this matrix A square equals to I. Now what you can say in this case? What are the eigenvalues of this matrix? 1 or minus 1, right? Right. Now if lambda is an eigenvalue of A, then lambda square will be an eigenvalue of A square, right? So lambda square has to be equals to 1. So lambda is either plus 1 or minus 1, right? Now if you take this polynomial qx equals to x square minus 1. Now is this polynomial contains all eigenvalues as a root? What are the root of this polynomial? 1 and minus 1. So it contains all the eigenvalues as roots, right? And what is q of a square minus I? So this is 0, right?
Yes, sir.
Okay. Now, so it, so from this last property, minimal polynomial will always divide this polynomial qx, right? So what are the possible cases for mx? The only possible cases are either it will be x minus 1. So you can write this x square minus 1 as x minus 1
Minus 1 x plus 1.
x plus 1. So the only possible case is x minus 1 x plus 1. There is no other possible case for minimal polynomial, right? So if after looking at this polynomial, what you can say? A is
A is diagonalizable.
yeah, right? So can you see how minimal polynomial is strongly connected with diagonalizable? Like in many cases, We don't need to look at the matrix. We just need the how its minimal polynomial is. Once you have the minimal polynomial, you can say many things about the matrix. Okay, let me ask you one question. Okay, suppose you have matrix A, and the matrix eigenvalue lambda is an eigenvalue for this matrix A, right? So in minimal polynomial, okay, let me write first characteristic polynomial. You will have the characteristic polynomial will be like x minus lambda to the power r into something, some polynomial, right? And this r is the algebraic multiplicity, right? So if you have x minus lambda to the power r, then lambda will come at r times, right? So that is the algebraic multiplicity, right? And you already know what is the geometric multiplicity of lambda is always less than equals to algebraic multiplicity of lambda, right? And it is always greater than equals to 1. Now if you write minimal polynomial will be x minus lambda to the power some r1 into some part. Okay, now this r1 will always be greater than equals to 1, because if you take r1 equals to 0, then lambda will not be a root of mx. So r1 has to be greater than equals to 1. Now the question is, what can you say about, now can you say r1 is greater than equals to geometric multiplicity of lambda? Think a little bit about this and you will get the
Yes,
answer.
sir, because
Yes.
yes, sir, since R1 is arithmetic multiplicity of lambda, so it will be greater than equal to geometric
No.
multiplicity.
This is not the algebraic multiplicity. Okay, let me write in different way. So this is minimal polynomial, and this is in x minus lambda to the power k, and into some part. Okay, now can this power k will be greater than equals to 1, and can you say k is greater than equals to the geometric multiplicity of lambda? It is not difficult to solve this, to give answer of this question. Think a little bit about this and you will get the answer. Okay, I can tell you the answer. Answer is no. Now can you give me an example for this? Okay, you take a matrix A. Okay, you take any diagonal matrix. Okay, any diagonal matrix 0 0 with two same eigenvalues. So you take 3 cross 3 matrix 2 2 1, right? Since it is diagonalizable, okay, what are the eigenvalues of this matrix?
2, 2, 1.
2 2 1, right? Now since this matrix is diagonal matrix, what can you say about the geometric multiplicity of 2? It will be equals to the algebraic multiplicity of 2, because it is a diagonal matrix. In diagonalizable matrices, algebraic multiplicity and geometric multiplicity both are same, right? So what is geometric multiplicity? 2, correct? Now what will be the characteristic polynomial of this polynomial, this matrix? The characteristic polynomial will be x minus 2 square x minus 1, right? Now what will be the minimal polynomial? The possible cases are either x minus 2 into x minus 1, and the
Or
another case is
x minus
x
2
minus
square
2
into x minus 1.
square x minus 1. Now I'm clearly saying this is not possible. So can you tell me why?
Because the matrix is diagonalizable.
Yeah, the matrix itself is a diagonal matrix, so it is diagonalizable. So the minimal polynomial has to be in the linear factorization. So this is not possible. So the only possible case is this one. So mx is equals to x minus 2, x minus 1. Now can you tell me what is the power of x minus 2? So in this case, what is the power of x minus 2? 1.
1. 1.
Okay, what is the power of x minus 2? Hello?
1.
1.
1.
Now what is the geometric multiplicity of 2?
2.
2. So 1 is always strictly greater than 2. Right? So this power may not be greater than equals to geometric multiplicity of lambda. Right? Of course, it is not equal, and it is also not greater than.
There will be not greater than sign.
Where? I'm saying this is not true.
Okay, okay.
Sorry. Okay. It was is this equals to this one, this greater than this one. Okay. Okay. Anyway, thank you. Okay. Now let me ask you the same question with the reverse inequality. Okay. Can you say k is less than geometric multiplicity of lambda? Okay, let me tell you the answer. So answer is no. Now can you give me any example? I think it is very easy to construct. You take a matrix A in which you are getting lambda 2 times as an eigenvalue. The geometric multiplicity of lambda is 1, and this matrix is not diagonalizable. Okay, let me give you the precise example. If you take this matrix 2 1 0 0 2 1 0 0 2, I think we have done this matrix before also. Okay, anyway, now what are the eigenvalues for this matrix? 2 2 2, correct? Now if you check the geometric multiplicity of this eigenvalue 2, it will be the nullity of a minus 2i, correct? Now if you calculate a minus 2i, so it will be 0 1 0 0 0 1 0 0 0. Now what is the nullity of this matrix? Okay, what is the rank of this matrix?
2, sir.
2.
The rank is 2. So what is nullity?
1.
1.
1. So the algebraic multiplicity is 1, right? So this matrix is not diagonalizable, right? Because the algebraic multiplicity of 2 is 3 and the geometric multiplicity is 1. Both are not same, so this matrix cannot be diagonalizable. Okay, now, so since it is not diagonalizable, so what is the characteristic polynomial for this matrix? X minus to the power 3, right? Now, what are the possible cases for minimal polynomials? So either x minus 2, x minus 2 to the square, x minus 2 to the power 3. Now, I'm saying clearly this is not possible. Why? Why this case is not possible?
So because a matrix is not diagonalizable,
Yeah,
therefore
correct.
it must be.
So, either this will happen or this will happen. In the both the cases, what is the power of x minus 2? In these both the cases, what is k? K is strictly greater than 1. But what is geometric multiplicity? 1. So in general, the powers of x minus lambda in the minimal polynomial and the powers of k, so this k may not be related with the geometric multiplicity. So when I read this eigenvalues and minimal polynomial first time, so at that time I thought, oh, maybe this k is the geometric multiplicity. So you should be think like that. Like, is this k equals to geometric multiplicity, or k is less than geometric multiplicity, or k is greater than geometric multiplicity? So actually, these two things are not related. Actually, this power had some relation with the Jordan blocks. Jordan canonical form, if you will read, then you will see this power has some relation with Jordan canonical form, Jordan blocks. This will actually give you the largest possible size of the Jordan block. Okay, so that you will see in the Jordan canonical form whenever you will read those things. Okay. Okay, with this, let me stop here. If you have any question, you can ask me. So I hope you have learned something new in this session. So if you have any question, you can ask me.
Sir, if I something found problematic in upcoming some days, can I mail the mail ID whichever you have shared with the
Yeah,
first
yeah,
class?
you can. You just
Okay,
you can put me an email. I will definitely reply.
okay. And I will may ask some problem something regarding this course.
You can
If
ask.
okay, sir. Thank you.
You can always contact me if you have any question or any doubt. Not in linear algebra, even I will be happy if you will ask something in real analysis and
Okay,
other
sir. Thank you,
areas.
sir.
Of course, I am not I'm not that much expert in differential equation and all those things. But for real analysis and linear algebra, you can ask me. I don't know you have
Sir,
differential
what kind of
equation or
questions generally come from this?
like that. You have to see the previous year questions. So some person told
Okay.
me in the last session for the minimal polynomials. So I have done minimal polynomials. But of course, diagonalizability is in your syllabus. Characteristic polynomial is also there. So I don't know about the minimal polynomial, but some person told me in the last session for minimal polynomial. So that's why I have done
Yes,
minimal.
yes. We have asked for the last lesson this, and this is help in though it is not clearly mentioned in the formal syllabus, but sometimes it may help in other questions.
But my intention is not to just write the result. Like in most of the time, what I do. So you should know how those results are coming. You should think about those things also. Like in some cases, of course, like even the okay. So somewhere I have written Kele Mintanthano. I don't know where I have written that. Okay, here now. So in this case also, you should think how to prove this. Even like you have two cases: A is diagonalizable and A is non-diagonalizable. For this case, it is very easy to prove. You should think how to prove this theorem if A is diagonalizable. That is not that much difficult.
Yes, sir.
Okay.
Okay, sir. Sir, I have one question in mind. Sir, we have already acquainted with the formal rule of multiplication of two matrices because it is row by column multiplication. Okay. And
Hmm.
sir, something I have written or I have noticed in some book or in some lectures note of unknown source that they are using also two other type of multiplication, and they are claiming that those two multiplication along with our known multiplication row by column or are equivalent, and those produce the same result. Something column by column multiplication, row by row multiplication, and sometimes they in some problem or in some theoretical proof, they are using row by row multiplication to visualize those things, and it is quite in some particular matrices these formal type multiplication quite difficult to visualize those things, and that is why they are using column by column multiplication or row by row multiplication. But in the book I have Friedberg and Inselspane type book. In those book I have not anywhere found this statement regarding this other type of multiplication.
See,
uh,
so for two matrices, you can define your own product, like something weird product you can define. No one is stopping you, and maybe
okay.
later that product will be related to many other things. Maybe that is the research, right?
Yes,
Like you define something like different from the existing thing, and if you
yes.
find that, oh, okay, this thing, the new thing is has some relation with the existing thing, that is the research, right? You can define your own product also.
Okay.
So like that this kind of case you can find many. Someone has defined some other product and someone has defined something new. So like this you can do also that.
Yes, I am verifying those two cross two for each multiplication, and they produce the same result.
So that's good, then you can use that product.
Okay, sir.
Like no one is stopping you. Like if something is valid, something is true, so then you can use that result. But like if you are using some other people's result, it should be like you should be careful, like that result should be correct. Like it may happen that you have taken some result from like unauthorized some paper or something, like some other book, and that result is only true for a special cases. So like you will be in trouble. So
Yes.
you should be careful if you are like these books, linear feedback and Hoffman Kunze, these are the standard books. Almost all the things in these books are correct because people have read these books many times and they didn't find any mistakes. So people believe that almost all the things in the book are correct. But if you are reading some book which is recently published, so that book may contain some mistakes and some errors. So you should be careful for those things. But if that book is like published by some standard publisher, then you can use those results.
Okay, sir. Thank you, sir, for clarification.
Okay, any other thing? Okay, if no questions, can I leave the meeting?
Yes, sir. Thank you so much once again for accepting our invitation and for all the sessions that you've taken. I am pretty sure that all the participants have found them resourceful and useful for their IIT JAM preparation. I also thank the participants for attending all the sessions. Thank you once again.
Thank you, ma'am.